Let me just quickly try and share, then we start. I need to share now. Okay. Thank you. Thank you. Okay, that is fine. We are on to lecture 6, which has to do with group 17 elements of the periodic table, and the group 17 elements of the periodic table are basically regarded as the halogens. They are regarded as the halogens, and they belong to the p block elements. The reason is because the last set of electrons in the octet are in the p orbital. They have 5 electrons in the p orbital, and they belong to the p block elements. And so they are generally known as the halogens. There are basically 6 elements in group 17, but we are emphasizing on 5. The 6 elements include fluorine, chlorine, bromine, iodine, astatine, and Tennessee. Astatine and Tennessee are basically radioactive. They have a short span, and so we are not going to emphasize much on them as we take the study this morning. So our emphasis will be on fluorine, chlorine, bromine, iodine, and some little statements about astatine. And so if you look at the table before you, you will see some physical properties of the group 17 element, which we call the halogens. The halogen, basically, they have 7 valence electrons. They have 7 valence electrons in their octet shell. And that is why the halogens only require 1 additional electron to have a full octet. And that determines their characteristics. So these particular characteristics of having of requiring only 1 additional electron for a full octet makes them to be reactive than other non-metal groups. Last lecture, we studied group 14 elements, and we said the difference in their properties is basically because of the transition from non-metals to metalloids to metals. But in this case, for the halogen, they are all non-metals. The only metals that would have been there, they are the astatine and the Tennessee. They are basically radioactive, and they have a short life span. So in their elemental states, the halogen.
No.
In their elemental states, the halogen, they form the atomic molecules, and the most reactive among them, let's just do a summary before we go into details. The most reactive among them is the fluorine, while the least reactive is the astatine and the Tennessee. So if you look at the table, the melting points at the boiling point, they increase down the table because of the van der Waals forces that existing between the atoms. The melting point, the boiling point, they increase as you go down the table because of the van der Waals forces that is existing between the atoms of the molecules of the halogens. And the size of the molecules also increases down the group. The size increases down the group. Why? Because of the addition of protons and neutrons. That will make the shares of the electrons to increase. And as the shares of the electrons increases, then there is need for additional energy levels. And that is why as you go down the group, the size of the molecules increases. Okay, and this increase in size, what it means is that there will be increase in the strength of the van der Waals forces as you go down the group. There will be an increase in the strength of the van der Waals forces as you go down the group. The atomic radius is expected also to increase down the group because of the addition of the number of protons and neutrons, okay, which will lead to more energy levels, and it will now lead to a larger orbital. So there will be an increase in the atomic radius, there will be an increase in the size of the atoms as you move down the group of the periodic table. The electronegativity decreases. If you look at that table, the electronegativity decreases down the group, while the ionization energy also decreases down the group, okay? Because for the ionization energy, you know, as you go down the group, the outer shell will be far away from the nucleus, and you will need less energy to pull out the electron from the resistance of the nucleus. So the ionization energy decreases down the group, electronegativity decreases down the group, and electron affinity decreases down the group, and the reactivity also will decrease down the group. So ionization energy, electron negativity, electron affinity, and reactivity of the elements, they all decreases down the group, okay? This is due to the distance of the outer shell from the nucleus. It is also due to the weak van der Waals forces that is existing between the atoms of the molecules, okay? Also due to the increase in atomic radius and the increase in size as you go down the group. These are the reasons why the electronegativity, the ionization energy, the electron affinity, the reactivity of the elements decreases down the group of the halogens. Now, let's quickly look at some information about bond formation in halogens. Bond formation in halogens. If you look at the halogens, they form ionic bonding with metals. They form ionic bonding with metals, and we call it ionic halides. We call it ionic halide. When the halogens react with the metals, maybe the chlorine, the fluorine, the bromine, the iodine, when they react with metals, they form ionic bonding with the metals, and we call them the product to be ionic halides. Okay, from halogen, you have halides. Okay, so, but also they have the ability to form covalent bonding with some metals, okay, that have a high charge, and the metals are small, the metal ions are small. Example of this is barium and beryllium and aluminium. Beryllium and aluminium, they form covalent bonding with the halogens. The reason is because the metal ions are very small in their size and they have a higher charge. So the halogens, some of them have the ability to form ionic bonding with metals, and they also have the ability to form covalent bonding with some certain metals whose size, ionic size are small, and they have a higher charge. Like I've mentioned before, the electronegativity, their electron affinity, their ionization energy, they all decreases as you go down the group. And I've given reasons why they are decreasing down the groups, okay? Because of the increase in size down the group, and because of the van der Waals forces that are existing between atoms of the molecule. So many iodides are covalent, and they have low melting points. Okay, they have exceptional cases of iodides that are covalent, and they have low melting points when you compare them to the fluorine. In terms of bond energy, the halogens, they are stable as diatomic molecule. They are more stable as diatomic molecules. So in their elemental state, halogens exist as diatomic molecules. Okay, they don't just exist as an atom because of its stability, but they exist in the elemental state as diatomic. When we say diatomic molecules, that means two of the atoms, okay, bonded together to form a molecule. So you have Cl2, you have Br2, bromine 2, iodine 2, chlorine 2, fluorine 2. So the bond energy for fluorine is exceptional from the rest, from all the rest diatomic molecules. Is abnormally low. The energy bonding is very low. Remember, we said that electroionization energy decreases down. We said electroaffinity decreases down. We said the electronegativity decreases down. So, which means fluorine is supposed to have a higher bond energy. But here we are saying that the bond energy of fluorine is abnormally low. Why? Due to the distance. The small distance between the two fluorine atoms, okay, which will lead to a repulsion between the low pairs. So we would have expected fluorine to have a higher bond energy, but here is exceptionally low. The reason is because the distance between the two fluorine atoms in the diatomic state is small, and that will lead to an electron repulsion between the low pair. This is the reason why fluorine is very reactive. Like I mentioned before, fluorine is the most reactive element in the halogen group, in the group 17. The reason is because it has a very small size. The size is very small, okay, and the distance between the two fluorine atoms that makes up the atomic molecule is very small. So it makes it to be very, very reactive. Okay, so the bonding that is existing in the iodide is stronger, even in the bromine, than in the fluorine. Okay, the bond that is existing in the bromine and in the iodine is stronger than in the fluorine. Okay, why? Because of the sp hybridization that is observed. Okay, because of the sp hybridization. So they have more stronger bonding than fluorine. So let's look at the oxidation states of this halogen. Remember, as a recap, we have said that the halogen elements of the group 17, they have 7 valence electrons. And so they require only 1 electron to form a full octet. And this is the reason why most of the halogen family, they exhibit a univalent ion. In other words, they exhibit an oxidation state of 1 in most cases. However, chlorine, bromine, iodine, they do exhibit higher oxidation states. But basically, most of them, they form a stable oxidation state of 1. Why? Because they require 1 additional electron to form a full octet. However, fluorine has a more stable oxidation state of 1, okay, because of the small size and because of the ability to easily accept 1 electron to form a full octet. Okay, so for chlorine, for bromine, for iodine, they have the ability to exhibit a higher oxidation state. And this depends on the level of their electronegativity. Remember, I said electronegativity decreases down the group. So chlorine, bromine, iodine, they exhibit oxidation, they can exhibit oxidation state apart from 1, they can exhibit oxidation states of +3, +5, and +7. They can decide to lose the entire 7 electron in the outer shell. Okay, in that case, they will not have +7 oxidation state. They can lose 5 of it, or they can lose 3 of it to have either +3 or +5 or +7. So chlorine, bromine, iodine have the ability to have higher oxidation states. Okay, and this is achievable, this is possible when electrons are promoted from the p share to the from the s share to the p share. Okay, even from S and P to the NTD orbital. So when electrons are promoted from the S to the P to the NTD orbital, they can exhibit a higher oxidation state of +3, +5, and +7, which is common with chlorine, with bromine, and with iodide. And when this happens, they easily form covalent bonds because of the paired electrons. Most of the halogens act as oxidizing agents. They act as oxidizing agents. Why do they act as oxidizing agents? Why do halogens act as oxidizing agents? Because they have the ability to gain electrons. They have the ability to gain electrons, and because of that, they act as oxidizing agents. And so they have the ability to oxidize metals. Halogen, because they act as an oxidizing agent, they have the ability to oxidize metals. And so most reactions involving the halogens are redox reactions in aqueous solution. Most reactions of the halogens are oxidation, reduction, reaction in aqueous solutions. So the fluorine, like I explained before, the fluorine, because of the small size, it has the ability to accept more electrons easily compared to fluorine, compared to bromine, compared to iodine. So fluorine is the strongest oxidizing agent. Fluorine has the strongest oxidizing, and the oxidizing power decreases down the group. Fluorine is the highest, while iodine is the least oxidizing agent. So you must take note of that, very important. Okay, so because of this, because fluorine is having a higher oxidizing power compared to chlorine, fluorine will displace chlorine from solution. So fluorine will displace chlorine, while chlorine will displace bromine, and bromine will displace iodine, iodide from solution. Why? Because of the difference in the oxidizing power, in their ability to oxidize. And that ability to oxidize, to act as an oxidizing agent, decreases down the group as you move from fluorine to iodine. Fluorine is the most or the strongest oxidizing agent. Okay, so these are the reasons why we use some of these halogens for extraction, commercial extraction of bromine from seawater. This is the basis. This is the reason why we have commercial extraction of bromine from seawater. Now, based on what we've just discussed on the ability of halogens to form oxidizing, to exhibit oxidizing power as oxidizing agents, okay, they have the ability to carry out displacement reaction. And I've explained to you that fluorine can displace bromine from solution, bromine can displace fluorine can displace chlorine, chlorine can displace bromine, and bromine can displace iodine from solution. The reason is because the oxidizing power, the ability to act as oxidizing agent, decreases as you go down the group. And so the halogen, they exhibit displacement reactions because of the ability to act as oxidizing agents. And the strength, the power of this oxidizing agent decreases down the table. I've explained this severally. And the reason for this is because of the size of the atoms. Remember, we said that the atomic radius increases down the group, the size of the atom increases down the group, because as you have more energy levels, the shares, the orbital shares will begin to increase. So the size, the atomic radius increases down the group. And because they increase down the group, the oxidizing power decreases down the group. Another reason is the attraction for electrons. The attraction from electron, the effect of the nuclear shielding from the octet share, the attraction of that is another reason why they can exhibit displacement reaction. So as you go down the group, the attraction for electrons decreases. It decreases. So the higher halogen will displace the lower halogen from their salt. And that is why I said that the fluorine ion will displace chlorine ion in solution, and while the chlorine will displace the bromine will displace the iodine from solution. Okay, so they have the ability to exhibit displacement reactions, very important. And the reason why they have the ability to exhibit displacement reaction is because of their ability to act as oxidizing agents. And the reason why they can act as oxidizing agents and carry out displacement reaction is because of the size of the atom and the attraction of electrons. This attraction of electrons decreases down the table, but the atomic radius increases down the table. Okay, so, and what you're having before you is examples of displacement reaction. And we've said that bromine can displace iodine in solution. And that is the first equation there. Okay, it can displace iodine in solution. And also chlorine can displace iodine in aqueous solution. So that is the reaction that you are having before you. Okay. You are going to get the slides so that you can have opportunity to go through and have more understanding. Okay, now let's look at the reaction of halide ions with halogen. Now I need to explain to you the difference between the halogens and the halide ions.
Because it will burn, eh?
The halogen atoms. Hey, mute yourself now. The halogens are the diatomic molecule that I talked about, the F2, the Cl2, the Pr2, and the I2. So in their elemental states, the halogens, they exist as diatomic molecules. Okay, but by the time they accept an electron, to have a full octet, they become ions, and we call them the halide ions. Okay, so we are looking at reactions between the ions from the halogens and the halogens themselves. When the ions interact with the halogens, this is what the table is trying to explain. So if the fluorine ion comes in contact with the fluorine atoms, the fluorine molecule, there will be no reaction. When the fluorine ion comes in contact with the chlorine molecules, no reaction. Okay, when fluorine comes in contact with any of the halogens, there will be no reaction. The same thing for chlorine. When the chloride ion, now we call it the chloride ion. We have the fluoride ion, we have the chloride ion. So when they accept electron to form a full octet, we will no longer just call them fluorine or chlorine. We'll call them the fluoride ion or the chloride ion, the bromide ion, the iodide ion. Okay, but in the elemental states, okay, as their atomic molecule, we call them fluorine, bromine, chlorine. And also you should be able to differentiate between a fluoride ion and fluorine. In the atomic states, they are fluorine, but when they accept electron to now form an ion, they become the fluorine, the ending of it will change from IDE, it will change to IDE, so it becomes fluoride ion, chloride ion, bromide ion, iodide ion. Okay, the last three letters will be changed with IDE to become, instead of fluorine, then we say fluoride ion. So you should be able to differentiate between ions and the atoms that makes up the molecule. So for the chloride ions, when they interact with fluorine, it will give you, that is the only reaction that is existing when the halide ions react with the halogens. When the chloride ion react with fluorine, they give you a pale yellow solution. But for the other halogens, there are no reactions. Okay. The same thing for bromine. Bromine cannot react. The bromide ion cannot react with the bromine. It cannot react with the iodine. No reaction. Okay. But the bromide ion can react with the fluorine, can react with the chlorine to give you yellow solutions. But the iodide can react with fluorine, bromine, and chlorine to give you a yellowish brown solution, as you can see from the table. But the iodide ion cannot react with the iodine. Okay, so you should be able to capture the table and understand it. Okay, let's quickly look at the reactions of the halogens, the reactions of the halogen. Like we've mentioned before, fluorine is the most reactive due to the low dissociation energy of the bond. Is the most reactive, the small size, the low energy level, okay, the low bond energy that is existing between the two fluorine atoms that makes up the atomic molecule. And so this results in stronger bonds with other elements. Okay, this results in stronger bond with the elements, and they can react with other elements at all. Fluorine can react with other elements except the noble gases. The noble gases, they are inert, they are not reactive. But fluorine can react with every other element. And their reactions are always very fast, very vigorous, and so in most cases, it is explosive. Like I mentioned before, I explained to you that the reactivity of the halogens decreases down the group. Their reactivity decreases down the group. And I've explained the reasons why there is a decrease in their reactivity down the group. The difference in the increase in atomic size, atomic radius, atomic size, and the difference in energy levels and all that. Okay, so in all this, fluorine is the most reactive and iodine is less reactive. And in most cases, it does not react with some elements. Okay, the fluorine, the chlorine, oxidize elements further than the bromine and the iodide. We've explained all that. So firstly, let's look at their reaction with water. Remember, we say reactivity decreases down the group. So how do they react with water? The halogens react with water, but the reactivities, like we mentioned before, decreases down the group. You come later, I have an online class. Okay. So later, I will round up by 11, so you come after 11. Okay, later. So all the halogens, they react with water, but the reactivity decreases down the group because the oxidizing power also decreases down the group. And so in this case, because fluorine is very strong oxidizing agent, is the most strongest oxidizing agent in the group, they oxidize water easily to molecular oxygen. Okay, so fluorine oxidizes water easily to form molecular oxygen, as you can see in that equation. Okay, while chlorine undergoes proportionation reaction, okay, with water to give you the hydrogen chloride and the hypochlorite. The hydrogen chloride oxidation state is -1, the hypochlorite is +1. So the fluorine is more reactive with water and the chlorine is less reactive. So that of the chlorine is disproportionation reaction, while that of the fluorine will easily oxidizes to give you molecular oxygen. So what about the reaction with sodium? All halogens, they combine with sodium to form sodium halides. The salts from the halogens are called halides. The ion are called halides ion. Okay, the salts that are formed when iodine reacts with other elements like metals, they form halides. And so all of them, they combine with iodine, with sodium to form sodium halides. So like we mentioned, the reactivity with sodium decreases down the group from fluorine to iodine. And you know the reason. The oxidizing strength decreases down the group the ionic size decreases and not that. So those are the reasons why there are variation in the reactions. And now, in the reactions with hydrogen, the reaction of fluorine is always very fast and explosive, even in the dark. At a very low temperature of minus 200 degrees Celsius, the reactivity of fluorine is explosive, even at very low temperature and in the dark, while chlorine reacts with hydrogen in the presence of sunlight, and the reaction is equally explosive. And so bromine also reacts moderately, and this time you have to heat with a catalyst, while iodine reacts slowly and reversibly, even on heating with hydrogen. So you can see that the reactivity decreases down the group. Fluorine is more reactive with hydrogen at very low temperature, even in the absence of light, while chlorine reacts in the presence of sunlight, and the reaction is also explosive. Bromine reacts moderately, but you have to heat with a catalyst, while iodine reaction with hydrogen is very slow, and such reactions are reversible even when you heat it. Now, reactions with non-metals. Halogens react with non-metals like phosphorus, okay, to form the salts, to form the halide of phosphorus and chlorine. So if you look at fluorine react with phosphorus to give you phosphorus pentafluoride, chlorine react with phosphorus to give you two oxidation state of 3 and oxidation state of 5, phosphorus trichloride and phosphorus pentachloride. The same thing with the bromine, the same thing with the iodine. So fluorine, the oxidation state is very strong. So fluorine reacts more with the non-metals because of its because it's the strongest of the oxidation state. So it oxidizes other elements to their highest possible oxidation states. But if you look at bromine, you look at iodine, they cannot oxidize other non-metals to their highest oxidation states. Okay, they can only oxidize because of their weak oxidizing power to oxidation state 3. Okay, but fluorine can oxidize other non-metals to the highest oxidation state of +5, while chlorine has the power to exhibit both +5 and +3 oxidation state in reactions with non-metals. Now, let's look at the reaction of the halogens with the alkalis. Okay, all halogens except fluorine, they undergo disproportionation reaction with the alkalines. Okay, so that means that fluorine does not undergo disproportionation reaction with the alkalines, but every other halogen they do. So they can exhibit oxidation states of -1 in one of the reactions, and in the other reaction of +1 in the other reaction. So the reactivity, like we have explained before, all the reactivity decreases down the group, all their reactions with the non-metals, with the alkaline, with the hydrogen, with water, all the reactions decreases down the group. Okay, they decreases down the group. Whenever halogens react with the alkalines, the product that is formed in the disproportionation reaction depends on the temperature of the reactions, and it depends on the type of halogen that is reacting. Remember, like we've mentioned, the reactivity decreases down the group. So at low temperature, you will see from here the reaction that is taking place, while at high temperature, you will also see the reactions that are taking place at these points. Okay, at low temperature, the bromine, and the iodide, their reaction is zero. The stability of the reaction is zero. But at higher temperature, it's only the iodide that has a zero tendency of reaction. So the stability of the product that is formed, okay, decreases out the group for the halogen oxygen reaction, okay, at oxidation state -1, while the other one that is at oxidation state of -5, that one increases down the group, but that of oxidation state -1 decreases down the group. So temperature determines the stability of the product that is formed in the reaction of halogen with the alkalis. Okay, and another reason is the nature of the alkali, the type of the halogen, the type of the halogen that is reacting. If the reaction of iodine is different from bromine, is different from chlorine, as you can see, at low temperature and at high temperature, the stability of the product differs. Okay, now we have what is called halogen oxoacids. That is the acids where you have halogen and presence of oxygen in the compound. And as you go down the group, the oxidation state also differs. Okay, so it differs. So the halogen, they form oxyacid with different oxidation states of halogens. Okay, the fluorine, we have 4 series of oxyacid that are known. Depending on the oxidation state, we have the hypohalous acids. Those one are oxidation state +1. We have the halous acid, the oxidation state is 3. The halic acid, the oxidation state is 5. The perhalic acid, the oxidation state is 7. So the strength of the acid decreases in that order from oxidation state 7 to oxidation state 1. So as you move from oxidation state 7 to 1, the strength of the acid decreases. Okay, so the strength of the acid is determined by the oxidation number. The higher the oxidation number, the higher the strength of the oxyacid that is formed with halogen. So let's briefly look at this oxyacid according to their oxidation state. We start with those oxyacids that have oxidation state 1, and we call them the hypohalous acid. So the only known oxyacid of fluorine, this is the only known oxyacid of fluorine. Okay, so the fluoride, the hypofluoride acid, the hypofluorous acid, this is the only known oxyacid of fluorine. So it is an unstable gas and it can easily decompose as the temperature increases into hydrogen fluoride and oxygen. Okay, but the other oxyacid of chlorine or bromine of iodine, they are in aqueous solution. And the most stable of these 3 is the hypochlorite. I will know the hypochlorite. The hypochlorite is our common bleach that we use in washing our clothes at home. And so all the hypohalous acid, including the bleach, they are weak acids. They are very weak acids. So in oxidation state 2 of the oxyacid, the only known oxyacid is the halous acid of chlorine, the chlorous acid at oxidation state +2. Okay, it exists in solution and it's a weak acid, but it is stronger than the hypochlorous acid. It is stronger than the bleach that we know of. Now we have another group, oxidation state 3, we call it the halic acid. Please remember these names. It can come out in your objective that what is the oxidation state, for example, of halic acids, or what is the oxidation state of halous acid, what is the oxidation state of hypohalous acids. So you can be asked, or you can be asked to give an example of an oxyacid of any of the halogens, or which of the following exhibit an oxidation state of 3. Okay, so please, you take note of them, it's very important. There are 3 known halic acid, oxyacid of oxidation state +3, we have the chlorates, the bromates, and the iodates. Okay, these are the three known acid at oxidation state +3. And the most stable among them is the iodates. It is stable at the chlorate, it is stable at the bromates, and they exist in solid form as white solid. So their solubility in water decreases down the group. And the last one is the oxidation state +7, and we call this the perhalic acids. Okay, an example of the perhalic acid is the perchloric acid. The perchloric acid is one of the strongest acid known. It's one of the strongest acids known, and it's a powerful oxidizing agent, and it can explode on contact, okay, with organic materials. Please, you come back after 11. I have lecture now. Okay, after 11, we just come. So the perchloric acid is the strongest acid that is known, and it's a powerful oxidizing agent and can explode on contact with organic material. If you bring perchloric acid close to cloth, to paper, or to wood, the reaction can be very vigorous and explosive. And so please take note of these characteristics. They are very important. So let us look at the strength, the relative strength of the halogen oxyacid. We'll be discussing the oxyacid of halogen. And we say the strength of this oxyacid depends both on the electronegativity and the oxidation states of the halogen. Remember, we said the electronegativity of the halogens decreases down the group. It decreases down the group. And we said the strength of the oxyacid depends on the oxidation state. The higher the oxidation state, the more stronger the oxyacid. So for oxyacid with halogen in the same oxidation state, the acid strength decreases. Okay, if they are on the same oxidation state, the acid strength decreases. Why? Because the electronegativity decreases. So if you have the chlorous oxyacid, the bromous oxyacid, the iodous oxyacid in the same oxidation state of +1 or +3 or +7, the acid strength decreases. Why? Because the electronegativity decreases. So the reason here for the difference in their strength is because of electronegativity. Because here we are not considering the oxidation state are the same. There is no difference in oxidation states. Okay, if we were to be a difference in oxidation state, we'll say that as the oxidation state decreases, okay, their acid strength decreases. But here they are in the same oxidation state. So the only factor that comes into consideration here is the electronegativity. For oxyacids, okay, of a given halogen, the acid strength decreases. I've explained that as the oxidation state of the halogen decreases. So if you are moving from oxidation state +7 to +5 to +3 to +1, then the acid strength decreases in that order. So there are two factors that determine the strength of an acid: the electronegativity and the oxidation state of the oxyacid. Is very important, very, very important. Okay. Then lastly for today is the interhalogen compounds. Interhalogen compounds. We're talking about the compounds that is existing between the halogens together when they interact, when they react with each other. Okay, the kind of halogens that are being formed. And there are 4 major classes of halogens that are formed when they interact with each other, depending on their this one is also determined by the oxidation states. Okay, they can react with each other to form oxidation state of 1, oxidation state of 3, oxidation state of 5, oxidation state of 7. Okay, so it depends on oxidation state. So you have the AS. When they react with each other, they can form a molecule with the compound formula of AS or AS3 or AS5 or AS7, and that also determines the oxidation state of the element. And remember that the reactivity decreases as you go down the group. So far in the lecture of today, let me give a recap because most of you did not join us at the beginning, and I want to do a brief summary of what we've learned so far. Now, we said that we've discussed today the group 17 elements, and the group 17 elements are the halogens. They are called the halogens. The halogens, they have 7 electrons in their outer shell. They are p-block elements, and so they only need one additional, come by 11. They only need one additional electron to form a full octet. And this characterizes their reactivity. This makes them to be more reactive than other non-metals. All the halogens, chlorine, fluorine, bromine, and iodine, they are non-metals. There are 6 elements in this group. There are 6 elements in this group, but the common are 5. You have fluorine, you have chlorine, you have bromine, you have iodine, you have astatine, and you have Tennessee. There are 6 elements that form the halogens. Okay, but astatine and Tennessee, they are radioactive and they have a short lifespan. So the emphasis of our discussion are basically the first 4 members of the group. And these are the fluorine, the chlorine, the bromine, and the iodine. So see, these are the core elements of emphasis. Okay, and we've said that in their elemental states, the halogens are more stable as diatomic molecules. What do we mean diatomic molecules? The fluorine can exist as a fluorine molecule F2, 2 of the atoms coming together to form a stable molecule. Okay, so they are more stable in the elemental state as a diatomic molecule. That is why if you are writing an equation, you write Cl2, you write F2, you have a bromine to Br2, high 2, because they are more stable as diatoms, as 2 atoms existing together to form a molecule. So the fluorine is more reactive, and we've explained why the fluorine is more reactive and the astatine is the least reactive. We're talking about reactivity in terms of their electronegativity, in terms of their small size, in terms of their atomic radius, and in terms of their electron affinity, their ionization energy. These are all the reasons that makes reactivity to be different. So fluorine is the most reactive, while astatine is the least reactive. So reactivity decreases as you move from the top of the table to the bottom because of the reasons that we've highlighted. And we said that most of the reactions of the halogens are redox reactions. They are redox reaction. Why? Because they have the ability to act as oxidizing agents. They have the power to oxidize. They can easily oxidize the metals. And because of this, most of their reactions in aqueous solution are reduction and oxidation reaction, redox reactions. And so we've said that the melting point, the boiling point, they increase down the group because of the van der Waals forces that is existing between the atoms of the molecules. We've said that the size of the atoms increases down the group, okay? And this increases the strength of the van der Waals forces as you go down the group. We've said the atomic radius increases down the group. And the reason why the atomic radius increases down the group is because of more of neutrons and electrons, more energy levels, more orbitals, and so the distance of the outer shell from the nucleus will continue to increase as you go down the group. And we say that the ionization energy also decreases down the group because of the valence electron that is far away as you go down the group from the nucleus. You need less energy to pull it out from the octet. So ionization energy decreases down, electronegativity decreases down, electron affinity decreases down, and these are all the reasons why all the reactions of the elements decreases down. So reactivity also decreases down the group. So these are the things that we've learned today concerning the group 17 elements. We've talked about the nature of the bond they form. They have the ability to react with metals through ionic bonding to form the ionic halides. They can also react with other metal ions that have a small size and higher charge, like beryllium, like aluminium, to form a covalent halide. Okay. And we also talk about the bond energy. I've mentioned that severally, that the energy of the bonding, like for fluorine, is small because of the small distance between the atoms. And we've also talked about the oxidation state, that because they need only one electron to form an octet, they commonly exhibit oxidation state of 1. Fluorine can exhibit an oxidation state of 1, while chlorine, bromine, and iodine, they have the ability to exhibit higher oxidation states, like oxidation state of 3 or 5 or 7. And the reason for that is because of the promotion of electrons from the s to the p orbital and from the p to the empty d orbitals to form covalent body. We've talked about the oxidation power, that the oxidation strength of the halogens decreases down the group. It decreases down the group, which means that fluorine has the highest or the strongest, the strongest oxidation agents. They have the ability to act as oxidation agent. Why? Because they have the power to gain electrons. Okay, so oxidizing power decreases down the group. And because of this, the higher halogen can displace the lower halogen. And so they exhibit displacement reaction. Fluorine can displace chlorine. Chlorine can displace bromine. Bromine can displace iodine. The reason is because oxidizing power decreases down, and so they can participate in displacement reactions. We've talked about that. We've talked about reactions with water. We've talked about reactions with the alkalines, with hydrogen, and all the other reactions. But the important thing that you must note here is that the reactivity decreases down the group. And most of the reactions of fluorine, because they are very fast and vigorous, they are often explosive, and this reactivity decreases down. So we've talked about reaction with water, reaction with sodium, reaction with hydrogen, reactions with non-metal, reaction with alkaline. We've talked about reaction with each other, reactions with, we've talked about the different type of oxoacid. Okay, we've learned about that, those in oxidation state 1, 2, 3, 4, and we said that the increase in acids on the acid strength of the oxoacid increases with increasing oxidation power, with the acid strength, with the oxidation power. Okay, so this is a recap of all that we have for group 17 elements. Okay, so if you have any questions, you can ask now as we close this lecture. The last lecture for this session will be coming up on Friday by 8 o'clock. Next tomorrow, Friday, 8 o'clock. So please let us all be there. We are going to have a brief test on Monday concerning all that we've learned in inorganic chemistry. We've been teaching organic chemistry for the last 3 weeks. And so we are going to have a short test on Monday for the inorganic that we've learned, okay, from the other 2 lecturers, including the one that I've taught you. And I'll round up this with radioactivity on Friday, 8 to 9. So please try and be there, okay, so that you can be able to, right? So we are going to have 3 tests, the test for physical chemistry, the test for inorganic, and the test for organic. After the test on Monday, the organic lecturers will come to take their lectures, and at the end of the organic chemistry lectures, you are going to have a test. So we are going to combine the 3 tests, and those 3 tests will amount to 40. We amount to 40 marks, okay, for your exam. So please take this seriously. It's no joke. We have up to 3,000 to 4,000 students that are supposed to attend this class, and we're only having less than 100 in every lecture time. Okay, so it's important to attend lectures so that you not come at the end of the day and start writing letters here and there that you prepare well for exam. And I'm not seeing how you are preparing well for your exam, and because most of you are not attending classes. What we have here for today is just about 66 students. Okay, so if you don't have any question, we'll close the class for now, and we'll see again on Friday. Thank you very much for those of you that have attended the lecture and can see that you're serious. I will take note of your attendance and we will work on it as time progresses.